Now we're going to look at the stereochemistry of the E2 elimination, and this specifically applies to when the alkene products can give E and Z isomers. And what we use to get the correct stereochemistry is the fact that the beta hydrogen and the leaving group must be anti-periplanar. So what does anti-periplanar mean? It means that they're both in the plane 180 degrees apart. Basically looking like this, where you have the hydrogen in the plane, your bond, and the leaving group in the plane. The hydrogen and the leaving group are on opposite sides 180 degrees from one another. This whole thing is especially important when your starting organohalide has chiral centers. So let's take, for example, this organochloride that has 2 chiral centers in it. And we're going to react this with sodium ethoxide. I'll use the solvent acetone, and I'm going to heat it just to make sure elimination is favored. So the sodium ethoxide is O-ethyl minus, that's a small base. So that's going to prefer this beta hydrogen, which will give the most substituted alkene. The only issue is that right now this hydrogen isn't in the plane. So my chlorine's in the plane where I want it. So basically what I'm trying to get anti-periplanar will be the chlorine, this bond, and then the hydrogen. So in order to get the hydrogen into the plane, I want to rotate the 3 groups at this chiral center here. So what I'm going to do is rotate the hydrogen into the plane, the methyl out, and the phenyl back. When I do that, let's redraw the molecule. Now everything on the right side will stay the same. We have the chlorine, hydrogen, methyl, but now I have hydrogen in the plane, methyl up, and the phenyl back. Through that rotation, I now have the hydrogen and the chlorine anti-periplanar. Now, if you actually like doing Fisher projections, you can also see this in a Fisher projection. If we view along this bond here, and I'll have the back carbon and the front carbon. On the back carbon, I have the chlorine straight up. Then I have the methyl and the hydrogen. On the front carbon, I have the hydrogen straight down, the methyl, and the phenyl. And you can see that the chlorine, my 2 carbons, and the hydrogen are all in the same plane. Now that we have these groups set up the way we want, we can use our base, which is the O-ethyl. And that is going to come and react with the beta hydrogen. We'll eliminate to give the double bond and lose the chlorine. So in the end, what we end up with is a new double bond. And then use your dashes and wedges to predict the double bond stereochemistry. So on the left carbon, I have a phenyl and a methyl. Well, since the methyl is on a wedge and the phenyl's on a dash, what we want to do is line up the groups on our other carbon in relation to those. So on my other carbon, my wedged group is a hydrogen. So it should be on the same side as the methyl. There's my hydrogen. And then my methyl group is the dashed group, and it should be on the same side as the phenyl. If you do that, you're going to end up with the correct stereochemistry at the double bond.